Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Today's problem focuses on a classic application architecture decision when moving to the cloud. Our company runs a popular gaming service that has two main parts: a web tier that users interact with, and a database tier that stores all the important game data. We are moving this to Google Cloud using an infrastructure as a service, or IaaS, model. This means we'll be managing the virtual machines ourselves. The question gives us some very important clues. The web tier needs to be load balanced. The database is sharded, meaning its data is split across several different disks. And the most critical clue of all, it is important that the state of the database tier is preserved. Let's figure out the right tools for this job. Identifying the correct solutions. This question is a select all that apply type. After analyzing the requirements, there are two correct answers that, together, form a complete solution. The first correct answer is stateful managed instance groups for the database tier. The keyword here is stateful. A database's entire job is to store and preserve state, the data itself. A stateful MIG is Google's specific tool designed to ensure that if a database VM is ever repaired or recreated, it always reconnects to its unique, persistent data disk, thus preserving the state. The second correct answer is load balancer and stateless managed instance groups for the web tier. The web tier is the opposite of the database. It should be stateless. Web servers are generally interchangeable. They fetch data from the database but don't store unique, permanent data themselves. A stateless MIG allows Google to automatically create, destroy, and scale these identical web servers, while a load balancer distributes user traffic evenly among them. These two answers together represent the best practice for a two-tier application. To understand this problem, we must understand the difference between stateless and stateful. Let's use an analogy. A stateless service is like a team of cashiers at a fast food restaurant. You can walk up to any cashier, and they can take your order. They don't need to remember you or your past orders. If one cashier goes on break, another can take their place seamlessly. The cashiers are interchangeable because the state, like the menu and prices, is stored elsewhere. This is perfect for web servers. A stateful service is like a classic bank with safe deposit boxes. Each box is unique and holds unique contents. If you want to access your box, you must go to the vault, and a teller needs the specific key for your specific box. The identity of the box and its contents must be preserved. If the bank just gave you a random box each time, it would be chaos. This is exactly how a database works. Each database virtual machine has unique data on its disk that must be preserved. This diagram shows the perfect architecture for our web tier. At the front, we have a cloud load balancer. Its job is to be the single entry point for all user traffic for our gaming service. Behind the load balancer, we have a stateless managed instance group, or MIG. An MIG is a powerful tool that manages a group of identical virtual machines. We call it stateless because the MIG treats these virtual machines like cattle, not pets. It automatically scales out by adding more virtual machines when traffic is high, and scales in by removing them when traffic is low. If a virtual machine becomes unhealthy, the MIG simply deletes it and creates a new, identical one from a template. Because the web servers themselves don't store any permanent data, any server can handle any request, making this model incredibly resilient and cost-effective. The stateful database tier. Now let's look at the database tier, which has completely different requirements. Here, we use a stateful managed instance group. At first glance, it looks similar, but there's a critical difference in how it operates. A stateful MIG gives each virtual machine a unique, permanent identity. As you can see in the diagram, we have instances named DB-MIG-01 and DB-MIG-02. More importantly, the MIG creates a stateful policy. This policy creates a permanent link between a specific virtual machine and its specific persistent disk. So, DB-MIG-01 is forever linked to database disk 01. If DB-MIG-01 fails a health check, the MIG will still automatically repair it. But instead of creating a random new virtual machine, it will create a new virtual machine that is also named DB-MIG-01, and it will ensure that this new virtual machine attaches to the exact same disk, database disk 01. This guarantees that the state, your precious game data, is always preserved, which is the #1 priority for a database. Analyzing the incorrect options helps clarify the concepts. Let's start with load balancer and stateful managed instance groups for the web tier. This is wrong because it's massive overkill. Web servers are meant to be interchangeable. Making them stateful would mean each web server gets a unique disk that it has to reconnect to, which adds unnecessary complexity, slows down scaling, and provides no real benefit. The other wrong answer is stateless managed instance groups for the database tier. This is not just wrong, it's dangerous. If you put a database in a stateless MIG, and the VM is recreated, it would get a brand new, empty disk. The original disk with all your data would become an orphan, detached from any VM. This would almost certainly lead to data loss and a catastrophic failure of the gaming service. You must preserve the state of the database, so a stateless MIG is the worst possible choice. One of the biggest benefits of an MIG is auto-healing, but it behaves differently depending on the type. On the left, for a stateless MIG, if a web server virtual machine fails its health check, the MIG's reaction is simple: terminate it. It then creates a brand new, identical virtual machine from the instance template with a fresh, empty boot disk. The old virtual machine and its disk are gone forever. Because the server was stateless, this is perfectly fine. On the right, for a stateful MIG, if a database virtual machine fails, the MIG's reaction is much more careful. It will still terminate the unhealthy virtual machine, but it will preserve the precious persistent disk that contains the data. Then, it creates a new virtual machine and, following the stateful policy, reattaches the original disk to this new instance. The result is that your database comes back online with its data intact. This is the core value proposition of a stateful MIG. Scaling also works differently between the two types of MIGs. For our stateless web tier, scaling is easy and is usually automated. We can set up an autoscaler that monitors CPU usage. When the average CPU across the group goes above, say, 75%, the autoscaler automatically creates new, identical web server virtual machines from the template to handle the load. When the load goes down, it removes them to save money. It's fully automated and hands-off. For our stateful database tier, scaling is a much more deliberate and usually manual process. You don't want a machine to automatically add or remove database servers. Adding a new database shard requires careful planning to provision its disk and rebalance the data. So while you can resize a stateful MIG, it's typically done by a database administrator who runs a command to increase the group size, then performs the necessary database operations. It's not something you would typically automate. So how does a managed instance group know what kind of virtual machines to create? It uses a blueprint called an instance template. An instance template is a reusable resource that stores all the configuration for a virtual machine, like the machine type, how many CPUs and how much RAM, the boot disk image, for example, Debian 11, any startup scripts, and network settings. Both stateless and stateful MIGs are built from an instance template. When you create the MIG, you point it to a specific template. Then, whenever the MIG needs to create a new instance, either for scaling out or for an auto-healing event, it refers back to this blueprint to ensure that every new virtual machine is configured identically. This guarantees consistency across all the instances in the group. The secret to how a stateful MIG can preserve data lies in understanding how Google's persistent disks work. A persistent disk is not part of the virtual machine itself. It is a separate, network-attached storage device that you can attach to and detach from virtual machines. Think of the virtual machine as the computer on your desk and the persistent disk as an external USB hard drive. You can turn off your computer, unplug it, and even replace it with a brand new one, but the data on your external USB drive remains safe. When you plug the drive into the new computer, all your files are still there. Persistent disks work the same way. Their lifecycle is completely independent of the virtual machine's lifecycle. This is what allows a stateful MIG to terminate a broken virtual machine and attach its disk to a new virtual machine without losing any data. Let's look at the actual G-Cloud commands to see how this is done in practice. The key difference happens when you create the managed instance group. First, you still need an instance template that defines your database virtual machine. Then, you use G-Cloud Compute Instance Groups Managed Create. You give it a name like DBMIG and set the size. The crucial part is the stateful policy. You use the command G-Cloud Compute Instance Groups Managed Set Stateful policy. You point it to your DBMIG, then you use the flag stateful disk. Here, you specify the device name, which is how the disk appears inside the OS, like SDB, and tell it to set auto delete to never. This is what tells the MIG, for any disk attached as SDB, preserve it no matter what happens to the virtual machine. This single command is what turns a regular MIG into a powerful stateful one. It's important to remember that the question specified an infrastructure as a service, or IaaS, deployment, which is why we're managing virtual machines ourselves. However, in the real world, there's often an easier option. Using a managed database service, which is a form of platform as a service, or PaaS. Services like Cloud SQL or Cloud Spanner are fully managed database services from Google. When you use them, you don't have to worry about managing virtual machines, instance groups, disks, auto-healing, or backups. You just ask Google for a database, and they handle all the underlying infrastructure for you. This dramatically simplifies operations and reduces the amount of work you have to do. For many companies, especially those that don't have a dedicated team of database administrators, using a managed service like Cloud SQL is often a better, more efficient choice than building a database from scratch on virtual machine. Let's do a final review of the core principles we've discussed. The architecture of your application tiers must match their function. Web tiers and other application front ends are typically stateless. They are designed to be interchangeable and can be scaled or replaced easily. The perfect GCP tool for this is a load balancer combined with a stateless managed instance group. Database tiers, and other systems that store unique data, are always stateful. Their identity and data must be preserved above all else. The perfect GCP tool for this is a stateful managed instance group, which guarantees that recreated instances will reconnect to their original persistent disks. Understanding this fundamental difference is one of the most important skills for designing robust and reliable applications in any cloud environment. Thank you for your attendance. Please consider subscribing to the channel.